There's a place on the moon where the sun never rises. Not the far side. The far side gets plenty of sunlight. It just faces away from Earth. This is different. This is a place where the geometry of the moon itself has kept the sun out for over 2 billion years. A crater floor 21 kilometers across, 4.2 kilometers deep. Colder than Pluto. Colder than the surface of Neptune's moon Triton. One of the coldest places in the entire solar system. And NASA wants to land right next to it. This isn't the moon that Apollo visited. Apollo went to the equator, flat basalt plains, broad horizons, full sunlight for the entire mission. Safe, predictable. The South Pole is a different world, rugged highland terrain, craters with 30-degree walls, boulders rolling down slopes, and a landscape split between eternal darkness and near eternal light, separated by a walk of less than 2 kilometers. Tonight on Stardrift FM, what's hiding in those dark craters? How 30 years of detective work found it, and why every spacefaring nation on Earth is now racing to the same 100 square kilometers of the moon. This is Stardrift FM. Let's begin. Apollo landed on the moon's equator, every mission. Apollo 11 through 17, all within about 26 degrees of the equator. And there's a reason for that. The equatorial regions are dominated by mere ancient lava flows that solidified into flat basalt plains billions of years ago. Smooth, level, wide open landing zones stretching for hundreds of kilometers, the terrain equivalent of a parking lot. And full sunlight. At the equator, the sun rises, crosses the sky over about 14 Earth days and sets. 14 days of light, 14 days of dark. Simple, predictable. You land at dawn, you have 2 weeks of sunlight to work. Now look at the South Pole. The moon's axis is tilted 1.54 degrees relative to the ecliptic. That's it, 1.5 degrees. Earth's axis is tilted 23.5 degrees, which is why we have seasons. Summer in the north means the sun stays high, days are long. Winter means the sun barely rises. The moon's tilt is so small that at the poles, the sun never climbs more than 1.5 degrees above the horizon. It traces a slow, low circle, just grazing the tops of ridges and crater rims. And anything below that line, any crater deeper than a few hundred meters, sits in permanent shadow. 324 of these permanently shadowed regions have been mapped on the moon. Over 300 larger than 1 square kilometer. The South Pole alone accounts for 13,600 square kilometers of permanent shadow, an area the size of Connecticut. And the temperatures inside, 25 to 40 Kelvin, minus 233 to minus 248 degrees Celsius. Colder than Pluto, among the coldest naturally occurring temperatures in the entire solar system. Apollo went to the moon in the light. Artemis is going into the dark. The detective story starts in 1994. Clementine, a joint Pentagon and NASA mission, orbits the moon and aims its radar at the permanently shadowed craters at the South Pole. Radio waves go in. Reflected signals come back to Earth. December 3, 1996. The Department of Defense announces that the reflected radar signal from the shadowed craters showed a pattern consistent with ice. Maybe. Other scientists argued the same radar pattern could come from rough rocks. The evidence was suggestive, not conclusive. 1998. Lunar Prospector, a small, cheap spacecraft with a neutron spectrometer. It doesn't look for ice directly, it looks for hydrogen. When cosmic rays hit the lunar surface, they knock neutrons loose. If there's hydrogen in the soil, those neutrons slow down. Fewer fast neutrons bouncing back means more hydrogen below. Lunar Prospector detects suppressed neutron flux at both poles. Hydrogen is there. An estimated 600 million metric tons of water ice mixed into the regolith at both poles combined. But here's the problem. Hydrogen isn't necessarily water. It could be implanted by solar wind. Could be bound in minerals. The evidence keeps building, but nobody can say for certain. Is there ice? July 31st, 1999. NASA crashes Lunar Prospector into Shoemaker Crater at the South Pole on purpose. The idea, the impact will kick up a plume of debris, and if there's ice, Earth-based telescopes will see the water vapor. They see nothing. The crash was probably too small, but the null result adds doubt. 2008, India's Chandrayaan-1, ISRO's first deep space mission. And aboard it, a NASA instrument called the Moon Mineralogy Mapper, M3, a near-infrared spectrometer that maps minerals by the wavelengths of light they absorb. September 24, 2009. 3 papers published simultaneously in Science. 3 different instruments on 3 different spacecraft, M3 on Chandrayaan-1, the deep impact probe during a lunar flyby, and archival data from Cassini. All detect the same absorption signature, wave lumps consistent with hydroxyl and water molecules on the Moon. Triple confirmation from independent instruments, the breakthrough moment. But M3 couldn't distinguish between water molecules and hydroxyl bound to minerals. Close but not definitive. And then NASA decided to hit the Moon hard. October 9, 2009, the LCROSS mission. A 2,300-kilogram Centaur upper stage slams into Cabeus crater at the South Pole, 2.5 kilometers per second. The impact excavates 350 metric tons of lunar material and blasts it into a plume above the crater rim, into sunlight, where the LCROSS shepherding spacecraft, flying 4 minutes behind, flies straight through it with spectrometers running. November 13, 2009, NASA's announcement? Not maybe, not suggestive, water. 5.6% by mass in the regolith. In some spots, mostly pure ice crystals. And not just water. The plume contained a cocktail of volatiles. Carbon monoxide, carbon dioxide, ammonia, methane, mercury, sodium, even traces of silver. 20% of everything blasted out of Cabeus was volatiles. The Moon isn't a bone-dry rock. It's chemically active. It has a water cycle of its own. 2018, Lee and Alphick publish in the Proceedings of the National Academy of Sciences, reanalyzing the M3 data with better methods. 3 specific spectral signatures at 1.3, 1.5, and 2.0 micrometers, matching the unique near-infrared reflectance of water ice. Not hydroxyl. Water ice on the surface, in the top few millimeters. Patchy. Possibly ancient. Definitive. 24 years from maybe to yes. From a radar hint in 1994 to surface ice confirmed in 2018. How much is there? Current estimates over 600 million metric tons, roughly 240,000 Olympic swimming pools of water, spread across thousands of square kilometers of permanently shadowed craters, not uniform patchy, concentrated in specific cold traps. Some spots ice-rich, most only modestly enriched. But it's there, and it changes everything. 3 sources, all of them contribute. Comets and asteroids. During the late heavy bombardment, roughly 3.9 billion years ago, water-bearing objects slammed into the Moon. Some of that water survived the impact and migrated across the surface until it found a cold trap at the poles. The volatile cocktail LCROSS found, the carbon monoxide, the ammonia, the methane, the mercury, matches the composition of cometary material. Impact delivery is probably the dominant source. Solar wind. The sun constantly blasts the Moon with protons, hydrogen ions. Those protons hit the oxygen atoms and silicate minerals on the surface and produce hydroxyl and water molecules, tiny amounts. In the top few nanometers of soil grains, M3 even detected that this water signal varies with time of day, stronger in the morning. An ongoing production cycle. Small quantities, but constant. And volcanic outgassing during the Moon's volcanically active period, 3.9 to about 1 billion years ago. Eruptions released water vapor from the interior. Apollo astronauts brought back volcanic glass beads containing trace water up to 46 parts per million. The Moon's interior isn't dry. It never was. Water molecules on the Moon move in a strange way. No atmosphere to carry them. They hop across the surface in ballistic arcs, kicked up by sunlight, flying a few kilometers, landing, getting kicked up again, wandering, until up into a permanently shadowed crater. And at 25 Kelvin, the sublimation rate is effectively zero. The molecule freezes to the floor and stays there for billions of years. Some of the water trapped in those craters may be older than life on Earth. Trapped in the dark, waiting. Now the counterpoint. Kilometers from the darkest place on the moon, there are ridges that almost never see shadow. The Connecting Ridge, a 14-kilometer strip of terrain stretching from Shackleton's western rim to de Gerlache crater's eastern rim. Illuminated 92 to 96% of the time. Near constant sunlight. Near constant solar power. Shackleton's rim itself, 86 to 89% illumination. Malapert Mountain, 120 kilometers away, 80 to 89%, and permanently visible from Earth, which makes it ideal for a communications relay. Do true peaks of eternal light exist? Places with 100% continuous sunlight? No. The moon's 18.6-year nodal precession cycle creates variations. Even the best spots endure shadow periods of up to 101 hours. But 92 to 96% is close enough. Solar panels on the Connecting Ridge would lose power for a few days every few months. Manageable with batteries. And here's the extraordinary part. The distance between a permanently shadowed crater floor and a sunlit landing site on the Connecting Ridge is less than 2 kilometers. 521 permanently shadowed regions have been mapped in the Connecting Ridge area alone. Astronauts could walk from a sunlit landing site to the edge of a permanently shadowed region and back in under 2 hours. Traverse slopes under 15 degrees. 2 kilometers separate eternal darkness from near eternal light, ice from power. Resources from energy. That narrow strip is where we want to land, and there's nowhere else like it in the solar system. Water is oxygen and hydrogen. Split it with electricity, electrolysis, and 1 kilogram of water gives you 0.889 kilograms of oxygen and 0.111 kilograms of hydrogen. Oxygen for breathing. Hydrogen for rocket fuel. Both. From ice that's been sitting in a dark crater for 2 billion years? Right now, it costs roughly $1 million to deliver a single kilogram of anything to the lunar surface. A kilogram of water from Earth to the moon, $1 million. Every kilogram you can make on-site instead of launching from Earth saves that million. The extraction technology exists in concept. Heat icy regolith to 60 to 105 degrees Celsius. Water sublimates in vacuum. Capture the vapor, condense it, electrolyze it, store the oxygen and hydrogen as cryogenic liquids. Microwave extraction can penetrate a meter into the soil without digging. Efficiency, 90 to 97% water recovery. On Mars, NASA already proved the concept works. The MOXIE instrument on Perseverance split carbon dioxide from the Martian atmosphere into oxygen, TOS. 122 grams over 16 runs. Tiny, but proof that you can make what you need where you are instead of bringing it from home. The moon version would operate at industrial scale, tons, not grams. A crew of 4 for 1 year needs about 5.8 tons of water without recycling. With ISS-level recycling, 98% recovery, that drops to about 117 kilograms of makeup water per year. But rocket fuel is where it gets transformative. A lunar ascent vehicle needs 10 to 30 tons of propellant. A full mission architecture, 30 to 100 tons. All of it potentially producible from lunar ice. One study estimates a single human Mars mission could save $12 billion using lunar-sourced propellant instead of launching everything from Earth. This isn't about collecting science samples. This is about making space travel sustainable. The ice trapped in those dark craters isn't just scientifically interesting. It's the economic foundation for everything that comes after. The most valuable substance in the solar system. Not because it's rare, but because of where it is. August 2026, 5 months from now. China launches Chang'e 7 on a Long March 5 rocket from Wenchang, Hainan Island. It's the most ambitious lunar mission any nation has attempted since Apollo. 5 components in a single launch. An orbiter with 8 scientific instruments. A lander with 7. A rover based on the proven U-2 design carrying ground-penetrating radar and a Raman spectrometer. And the most important piece, a mini flying hopper probe. 18 payloads total. The landing site, the illuminated rim of Shackleton Crater. Coordinates 123.4 degrees east, 88.8 degrees south. Shackleton. The same crater, the same South Pole, the same spot that's on NASA's list of candidate Artemis landing sites. And the hopper is the crown jewel. It launches from the lander on Shackleton's sunlit rim, flies at least 10 kilometers using rocket propulsion, into a permanently shadowed crater, into the dark, where it's 25 Kelvin and no sunlight was reached in 2 billion years. It lands using active shock absorption technology, then it crawls away from its own landing disturbance. The rocket exhaust would have scattered the surface material using legs, moves to undisturbed soil, drills into the regolith, and analyzes what it finds with the LU instrument, a mass spectrometer that can detect water molecules and measure hydrogen isotope ratios. Those isotope ratios aren't just data points, they tell you where the water came from. Cometary ice has a different deuterium to hydrogen ratio than water produced by solar wind, different again from volcanic outgassing. The hopper won't just confirm the ice is there, it can tell us its origin story. Compare this to NASA's plan. Viper, the ice-hunting rover, was canceled in 2024, revived in 2025, and is now targeting late 2027. Delivered by Blue Origin's Blue Moon lander. Its first flight is conditional on Blue Moon working. Viper drives near the edges of permanently shadowed regions. It needs solar power. It can't go deep into the dark. The hopper flies into the dark. Artemis IV, the first crewed landing, targets 2028. Chang'e 7 arrives in August 2026, on track. If it works, if the hopper enters a permanently shadowed crater at Shackleton and confirms substantial water ice, China becomes the first nation to directly characterize lunar water in situ, on the same crater rim where Artemis wants to land. 2 nations, same crater, same darkness. One arrives in 2026, the other is still building. This isn't the moon we remember from Apollo photographs. Flat, gray, unchanging. A place we visited, planted a flag, collected some rocks, and never went back to. The South Pole is something else entirely. A landscape of extremes. Eternal darkness hiding ice that might be older than any life on Earth. Near eternal light offering power for anyone who can land in the right spot. And a narrow strip between the two where the entire future of human space exploration might be decided. The ice trapped in those craters could be the key to everything. Breathing on the moon. Fueling rockets without launching from Earth, building a sustainable human presence beyond our planet, making Mars reachable. But first, somebody has to go into the dark. Walk to the edge of a crater that hasn't seen sunlight in 2 billion years. Drill into the regolith and find out what's really there. A hopper from China will try in August. A rover from NASA might follow a year later. And eventually, humans, standing on the rim of Shackleton, looking down into a darkness that predates everything they've ever known. Now you know where we're going. Next time, how we get there. And why landing on the South Pole might be the hardest thing NASA has ever attempted. This is Stardrift FM. Keep drifting.